The universe likes to play tricks on us. We build our models, we write our equations, we convince ourselves we understand how reality works, and then something comes along that makes every physicist in the room go quiet. Some of these things are natural wonders, some are man-made inventions, and some are straight-up unsolved mysteries that have stumped the greatest minds on the planet for decades. Today we're counting down 15 of the strangest phenomena that seem to break the rules of physics as we know them. Buckle up, because reality is about to get a lot weirder. You'd think the closer you get to a fire, the hotter it gets. That's basic common sense, and it's true almost everywhere in the universe, except, apparently, on the sun. The surface of the sun, called the photosphere, sits at around 5,500 degrees Celsius. But if you travel outward, away from that surface, into the sun's outer atmosphere, known as the corona, the temperature doesn't drop like it should. Instead, it skyrockets to over 1,000,000 degrees Celsius. That's hundreds of times hotter than the surface itself, and nobody has a fully agreed-upon explanation for why. This puzzle is known as the coronal heating problem, and it has haunted solar physicists since the 1940s. The leading theories involve magnetic reconnection, where twisted magnetic field lines snap and release enormous bursts of energy, and something called nanoflares, tiny explosions too small and too frequent to observe directly, but possibly numerous enough to superheat the corona. Whatever the true cause, it's a humbling reminder that the star keeping us alive still holds secrets it hasn't given up. Invisibility has always been the stuff of fantasy novels and comic books, but modern materials science has actually made real progress toward it. Scientists have developed what are called metamaterials, engineered structures with properties not found in nature, specifically designed to manipulate electromagnetic waves. Some of these materials can bend visible light around an object rather than letting it bounce off, which means the light that reaches your eyes looks as though the object simply isn't there. Several companies and research labs, including projects backed by military interest, have built early camouflage fabrics based on similar light bending and light redirecting principles. They're not yet full Harry Potter-style invisibility cloaks, but the underlying physics is real, and it's advancing fast. It's strange to watch something once considered pure magic slowly turn into an engineering problem that determined scientists are actually solving. Absolute zero, measured at 0 on the Kelvin scale, is supposed to be the coldest temperature possible, the point where atomic motion theoretically stops completely. It's treated as a hard floor, a wall that nothing can go past. Yet in 2013, physicists in Germany managed to create a gas of potassium atoms that technically existed at a temperature below absolute zero. This doesn't mean the atoms were colder in the way you'd normally think about cold. Instead, the researchers manipulated the system so that it existed in a bizarre energy state where adding energy actually made the system behave as though its temperature were negative on the Kelvin scale. It sounds like nonsense, and in a very real sense it breaks our everyday intuition about what temperature even means, but the mathematics checks out under quantum statistical mechanics. These negative temperature systems could one day help scientists better understand energy and engines, but for now they remain one of the strangest curiosities in modern physics. We tend to think of gravity as the dominant force of the universe, the one holding planets in orbit and galaxies together. But zoom down to the scale of subatomic particles, and gravity becomes almost embarrassingly weak compared to the other fundamental forces, electromagnetism, and the strong and weak nuclear forces. In fact, gravity is roughly 10,000 trillion times weaker than electromagnetism at that scale. This massive imbalance is known among physicists as the hierarchy problem. It's tied closely to the discovery of the Higgs boson, the particle responsible for giving other particles their mass. If mass and gravity are supposed to scale consistently across the universe, gravity's dramatic drop-off at small scales shouldn't happen, and yet it does. Solving the hierarchy problem is considered one of the biggest open questions in theoretical physics, with proposed answers ranging from extra, hidden dimensions of space to entirely new families of undiscovered particles. Here's a genuine head-scratcher about the universe. Matter and antimatter should have been created in exactly equal amounts during the Big Bang. Since matter and antimatter annihilate each other on contact, releasing pure energy, a perfectly balanced universe should have wiped itself out almost instantly, leaving nothing but light. Obviously, that didn't happen, since you're reading this right now made of ordinary matter. One possible piece of the puzzle is a hypothetical particle called the Majorana fermion, first theorized back in 1937, which would be its own antiparticle, meaning it could interact with and effectively cancel out a version of itself. If Majorana particles existed and behaved a certain way in the early universe, they could help explain why matter ultimately won out over antimatter. Catching direct evidence of this behavior is incredibly difficult, since the predicted interaction is estimated to occur once every 100 trillion years across the entire cosmos. Even so, scientists have created quasiparticles in laboratory conditions that mimic Majorana-like behavior, and these are now being explored for use in next-generation quantum computers because of their unusual stability. If you've ever seen a demonstration where a small aluminum boat appears to hover motionless in midair inside a glass tank, you've witnessed one of the most satisfying tricks in science education. It isn't magic, and it isn't a hidden wire. The tank is filled with sulfur hexafluoride, a gas roughly 5 times denser than the air we normally breathe. Because the aluminum boat is less dense than this heavy gas, it simply floats. On top of it the same way a real boat floats on water, except the water here is completely invisible to the naked eye. Sulfur hexafluoride has another famous party trick, too. Since it's so much denser than normal air, it does the exact opposite of helium to your voice. Instead of making you sound squeaky and high-pitched, inhaling it, which, for the record, should only ever be done under strict safety supervision, drops your voice down into a deep, booming register. It's a fantastic, low-cost way to demonstrate real physics that looks completely impossible at first glance. Imagine bending a piece of wire into a tangled, crumpled mess, then applying a little heat and watching it spring back perfectly into its original shape as though it had a memory of its own. That's exactly what happens with nitinol, a nickel-titanium alloy first developed by U.S. naval researchers in the 1960s. Nitinol belongs to a category of materials called shape memory alloys. At a microscopic level, the metal's crystal structure can shift between 2 different arrangements depending on temperature. Bend it while it's cool, and it holds the new shape. Heat it back up, and the crystal lattice snaps back to whatever form it was originally trained into. This isn't just a neat party trick. Nitinol is used in medical stents that can be compressed for insertion into the body and then expand into place once they warm to body temperature, in eyeglass frames that can be twisted and still return to shape, and even in aerospace engineering. A metal with a memory sounds like science fiction, but it's sitting in hospitals and product catalogs right now. Nearly 2,000 years ago, a Greek engineer named Hero of Alexandria built a fountain that appeared to run forever without any pump or outside power source. Water would shoot upward from a spout, seemingly powered by nothing at all. In reality, Hero's fountain is a brilliant demonstration of air pressure and the movement of fluids between sealed containers, not a violation of any physical law. The device uses 3 connected vessels. As water falls from an upper container into a sealed lower one, it pushes trapped air through a tube into a third container, and that pressurized air forces water up through a spout. It looks like perpetual motion, but it isn't. The fountain will eventually run out of usable energy and stop. Physics teachers still build simple versions of Hero's fountain today, usually with nothing more than plastic bottles and tubing, because it's one of the most elegant, hands-on ways to teach students about pressure differentials without a single moving mechanical part. A waterfall, by definition, should send water crashing downward. So the existence of reverse waterfalls, where water appears to be blown back up a cliff face instead of falling off of it, seems like it shouldn't be possible. Plenty of viral videos claiming to show this effect are exaggerated or outright faked, but genuine reverse waterfalls really do exist in places like Chapman's Peak in South Africa and certain cliffside spots in India during monsoon season. The explanation comes down to a straightforward battle between 2 forces: gravity pulling the water down, and powerful updrafts of wind pushing it back up. When wind speeds at a cliff edge are strong enough to match or exceed the force of gravity acting on the falling water, that water gets caught midair and blown backward, sometimes turning into a fine upward mist. It's a rare combination of geography and weather, but when it happens, it's one of the most visually stunning displays nature has to offer. Twice a year, In a narrow band of locations near the Earth's tropics, something happens that has genuinely startled people throughout history. Known in Hawaii as Lahaina noon, this phenomenon occurs when the sun passes directly overhead at solar noon, positioned at an angle of exactly 90 degrees relative to the ground. For a brief window, vertical objects, poles, people, buildings cast no shadow at all. Since our brains are so accustomed to constantly, unconsciously processing shadows as a cue for depth and time of day, a shadowless landscape can feel deeply unsettling, almost like reality is glitched. There's nothing supernatural happening. It's simple geometry involving the Earth's axial tilt and the observer's latitude. But before people understood the astronomy behind it, this vanishing shadow effect understandably caused a fair amount of confusion and unease. It remains a striking, rarely witnessed reminder of just how strange our familiar physical world can look under the right conditions. In the village of Krishnagiri in Tamil Nadu, India, sits an enormous granite boulder perched on a smooth, sloped hillside at a seemingly impossible angle. Local legend says it's a dollop of butter dropped by the god Krishna, and it's affectionately known as Krishna's butterball. Weighing an estimated 250 tons, the rock has sat in the exact same precarious position for centuries, maybe far longer, without ever tipping or rolling despite its position on a slippery, inclined surface. Nobody knows exactly how it got there or how long it's been in place. In the 1900s, a colonial governor reportedly tried to have it moved using 7 elephants, without success. Geologists suspect the boulder is a natural result of erosion over millions of years, slowly whittling away the surrounding rock until this particular formation was left balanced on its unusual perch, with friction and its precise center of gravity keeping it locked in place. Local kids treat the smooth slope beneath it as a natural slide, seemingly unbothered by the multi-ton rock looming above them. Travelers passing through Cairo International Airport have stumbled across an art installation that looks like it's breaking the laws of gravity outright. One large stone sits flat on the ground while a second, similarly sized stone hovers above it, connected only by a thin strand that looks more like a piece of rope than any obvious support. Structure. Unlike some of the ancient mysteries on this list, this one has a clear, documented explanation. The installation is a sculpture by the acclaimed Egyptian artist Shaban Abbas, who built it using powerful concealed magnets combined with a rope-like structure specifically to balance the upper stone's center of mass in a way that keeps it stable and suspended. Magnets can shift how weight is distributed across an object, and Abbas used that principle to create something that looks genuinely magical to anyone unfamiliar with the trick. It stands as a great reminder that even the most convincing, impossible sights are often the product of clever, intentional engineering rather than an actual break in the rules of physics. Since the early 1990s, scientists tracking spacecraft as they use Earth's gravity for a speed boost, a maneuver called a gravity assist or flyby, have noticed something they can't fully explain. In several documented cases, spacecraft including NASA's Galileo, NEAR, Rosetta, and Cassini probes gained a tiny, unexpected burst of extra velocity during their flybys, amounts too small to matter for everyday purposes, but far too large to be explained by measurement error or by any force scientists currently understand. This is known as the flyby anomaly. According to the basic laws of orbital mechanics, a spacecraft shouldn't be able to pick up unaccounted for kinetic energy during a gravity-assisted flyby. Energy in these systems should be conserved exactly. Proposed explanations have ranged from atmospheric drag and thermal radiation pressure to more exotic ideas involving modifications to general relativity itself, but so far no single explanation accounts for every observed instance. Interestingly, more recent, more precisely tracked missions have shown smaller or no anomaly at all, leading some scientists to suspect improved measurement techniques may eventually resolve the mystery. For now, though, it remains an open and fascinating anomaly in orbital physics. Black holes already break plenty of intuitions about space and time, but one particular puzzle strikes at something even more fundamental: the black hole information paradox. In quantum physics, information, the complete data describing a particle's state, is believed to be fundamentally indestructible. It can change form, but according to the core principles of quantum mechanics, it can never truly be erased from the universe. Black holes seem to violate this rule. According to Stephen Hawking's own calculations from the 1970s, black holes slowly evaporate over immense timescales by emitting what's now called Hawking radiation, and this radiation appears to carry no information about what originally fell into the black hole. If that's true, then anything that falls in and all the information describing it would eventually be permanently lost when the black hole disappears, directly contradicting quantum theory. This contradiction has kept some of the greatest theoretical physicists on Earth working for decades, with proposed resolutions ranging from information being stored on the black hole's boundary, an idea called the holographic principle, to more radical theories involving wormhole-like connections known as ER=EPR. It remains one of the most important unresolved problems at the intersection of gravity and quantum mechanics. There's an old saying that a watched pot never boils, and while that's just a figure of speech in everyday life, something remarkably similar turns out to be scientifically real at the quantum level. It's called the quantum Zeno effect, and it describes how continuously observing or measuring an unstable quantum system can actually slow down, or in extreme cases effectively freeze, its natural rate of decay. This was first theorized in the 1970s and later confirmed experimentally, including a well-known 1990 experiment led by physicists at the National Institute of Standards and Technology, where researchers showed that frequently measuring trapped ions suppressed their expected transitions between energy states. The effect has since been reproduced by independent research teams around the world using different quantum systems. Essentially, the very act of measurement forces a quantum system to reset its wave function, and if you measure often enough, the system barely gets a chance to evolve toward decay at all. It sounds like something pulled straight out of science fiction, but it's a real, well-documented consequence of quantum mechanics, and it may eventually play a meaningful role in quantum computing and quantum error correction. Every one of these phenomena is a reminder that the universe still has plenty left to teach us. Some, like the Cairo sculpture or the sulfur hexafluoride boat, turn out to have elegant, fully understood explanations once you look closer. Others, like the coronal heating problem or the black hole information paradox, remain genuinely open questions that could reshape our understanding of physics entirely once they're finally solved. Which one of these do you find the most mind-bending? Let us know in the comments, and if you enjoyed this journey through the strangest corners of science, stick around. There's always more of the universe left to explore.